The next operation we're going to look at is divergence. And so we can find divergence of a vector or vector field. So the divergence of a vector field A at a given point P is the outward flux per unit volume as the volume shrinks about point P. So again, just like with our gradient, that was a bit of a mouthful. So let's write a mathematical equation to kind of summarize this, and then we'll come back in a little bit and talk about a clear physical interpretation. So first of all, we can write the divergence of A as div A, so a little shorthand there. And this is going to be equal to our del operator dot A. So we're using our dot product. And sort of adapting our written equation above here to a mathematical equation, we have the limit as our volume, so we're say delta V is our volume, is going to 0 of, now we're talking about outward flux. So as we said before, we can use a surface integral over a closed surface of A dot ds. So we've talked about that a little bit in a previous video, and we're going to divide that by our volume delta V. So in this equation, again, just to be explicit, our delta V is a volume enclosed by a surface. So enclosed by surface S, and within that volume is where P is located. Okay, so a couple of things to note before we get into sort of a more rigorous definition of our divergence is that because we're using a dot product, this is going to result in a scalar field. So resulting in a scalar field, so kind of the opposite of our gradient. Remember, we operate a gradient. We're using the del operator on a scalar field and we get a vector as a result. Here we're using our del operator on a vector field and we're getting a scalar field as a result. So now more about our physical interpretation. So we can think about our divergence of A as a measure of how much the field originates from a point P. So div A at point P, so let's say that is a measure of how much the field, or a field, doesn't necessarily have to be just one, originates from the point. And so in order to make that a little more clear, let's look at a few different drawings of sort of a few different scenarios, keeping this idea in mind about a field originating from a point. Okay, so let's say we have some point P in space, and so let's say at that point P we sort of measure a field, and again, we're not talking about anything specific, but this could be an electric field, a magnetic field, whatever type of field, a force field. And so let's call our field A, and so let's say we have our field A sort of emanating in all directions from P like this. So this is our field A. So in this case, what we would have is we would have the divergence of A at P would be greater than 0. And so what that would indicate is we have a source point at P. And again, keeping in mind this definition of, so our divergence is sort of quantifying how much the field originates at that point. So a positive divergence indicates we have a field originating at a point P. So conversely, we could just flip all of these arrows around. So let's say we have this point P, and now we have some vector field A, which is sort of always pointing towards this point P. So again, this is our vector field A, just sort of switch directions. And so in this case, our divergence of A would be at point P. So divergence of A at P would be negative. So it'd be less than 0. And so we would say in this case, we have a sink point. And so of course, the third case would be as if we just have our point P and we have our vector coming in some cases. So maybe it's something like this from below. And then in this side, it's just going out in the opposite direction, such that sort of our net net change in our field at P is 0. We have some coming in from one side, some going down the other side. So in this case, our div A at P would just be 0. So again, we can kind of think of this divergence as a measure of how much we're originating our field or sort of terminating our field at that point. So we can sort of derive a more detailed equation for this, or I should say a more practical equation for this. And so in order to do that, let's consider a differential volume with our point P. And so we're not going to go through the whole derivative, but I want to at least sort of set it up so you can kind of know something important here, and we'll dig into this a little bit more in a later example. So we see this differential volume, which encloses our point P. And so what we want to do is, remember, we're concerned with our outward flux. So we want outward flux through this differential volume. In order to do that, in this case with our Cartesian coordinates, we want to consider the 6 faces of the cube. So consider 6 faces of our cube. So what we end up doing then is we of course are interested in this integral over the surface of A dot ds, where our A is of course our field. And so why do we want to do that integral? Well, if we come back up here to our rough definition, of course we have this integral here, which is related to that outward flux. So if we want to evaluate this for our differential volume shown above, what we end up doing is we end up doing sort of 6 separate integrals. So we have integral over the front face of the cube, plus the integral over the back face of the cube, plus the integral over the left, plus the integral over the right. And so these are all double integrals because we have a 2-dimensional surface, plus the integral over the top, plus the integral over the bottom. And so I've kind of run out of space, but all of those are A dot ds. So that A dot ds should be up here. So with each of those 6 integrals, what we're going to have to do then is they'll have different limits as we are sort of doing the surface. So for instance, if we're looking at our top surface, we would have limits of y and x at a certain z value. And each of these different integrals is also going to have a different ds. So we'd have to calculate that based on our differential surface area that we talked about when we were sort of preparing ourselves to do our integrals in a previous video. But again, we're not going to go through the details of that derivation. If you want to see more details about that, you could look on pages 76 and 77. Essentially what it involves is doing a Taylor series expansion in 3 dimensions, neglecting higher order terms, evaluating that integral, and what we see is that for our Cartesian coordinates, we get that our divergence of A is equal to the partial derivative of the x component of A with respect to x, plus the partial derivative of our y component of A with respect to y, plus the partial derivative of our z component of A with respect to z. So this is our divergence for our Cartesian coordinates. So similar analysis can be done for our cylindrical and our spherical, of course, and I'll write those equations. But before, let me just write for clarity that in this case, our A for our Cartesian coordinates would be AX in our X direction, plus AY in our Y direction, plus AZ in our Z direction. Okay, so now for our cylindrical coordinates, we have that the divergence of A is equal to 1 over rho times the partial with respect to rho of rho A rho. So A sub rho there is our rho component, plus 1 over rho times the partial of A sub phi, so that's our phi component, with respect to phi, and then plus the partial derivative of our z component of A with respect to z. And that is the equation for our cylindrical coordinates. So then finally for our spherical coordinates, we have that the divergence of A, so we're doing a dot product still, is equal to, so this is getting a little messier, So we have 1 over r squared times the partial with respect to r of r squared times the r component of a plus 1 over r sine theta times the partial with respect to theta of our theta component of a times sine of theta plus 1 over r sine theta times the partial of our phi component with respect to phi. And so that is our divergence equation for our spherical coordinate system. And again, just like with our gradient, I don't expect you guys to remember these. I would expect you to have them in your note sheets or somewhere that you can reference, and of course to be able to use them. And we'll see how to do that in an example here in a little bit. The last thing I want to look at in this video is just some of the properties of the divergence of a vector field. So properties. So the first property we want to consider is, as we've said before, is that it produces a scalar field. And we said, of course, that is expected because we are using the dot product. The second property is if we have the divergence of the sum of two vectors. So divergence of A plus B is equal to the divergence of A plus the divergence of B. And the third and final property we're going to consider for our divergence is our product rule. So if we have the divergence of a scalar times a vector, V is a scalar, A is a vector, that's going to be equal to V times the divergence of A plus A times the gradient of V, because remember, gradient of V is giving us a vector value, so that's why we can do the dot product here. And so these properties are going to make our life a little bit easier as we're working with some of our later material, and oftentimes what we'll see is it can sort of provide a little shortcut to make things a little easier as well.